Welcome to section 1.4, the last section of chapter 1. So now we're going to talk about experiments. So things to look out for, to take notes on, are kind of the principles of experimental design. And also we're going to use, there's going to be a lot of different vocab for this section. So it's hard to put them all in here. So just know that we're going to start talking about experiments and start introducing some more vocabulary words. And then the difference between experiments and observational studies is going to be crucial. And yeah, that's what we're taking notes on. So, principles of experimental design. Control is you compare treatment to a control group. So control, treatment, we kind of talked about that in the first section with the case study. Okay, randomize. So a good experiment needs to have a randomization. Okay, randomly assign, you got to be randomly assigning subjects to treatment, and has to come from a random sample from the population whenever possible. As random as possible is maybe another way to say it. You would want a good experiment you should be able to replicate it. So if it's true for one sample, it should be true for another sample. And then blocking is when there are variables that are known or suspected to affect the response variable. Make sure that you have like equal proportions of that group. So for example, say you have something that where you suspect it affects women more than men, then blocking would be to make sure your treatment and control group both have equal proportions of men and women, so that that won't affect the thing you're looking for. Okay, so our first example here, we're going to talk more about blocking. So say we want to design an experiment to investigate if energy gels make you run faster. And I'm going to move myself up to the top here and a little out of the way so that, because the words are eventually going to get in the way behind me. All right, so treatment. You have some runners with energy gel. Control group, some runners with no energy gel. Okay, so then it's suspected that energy gel might affect pro and amateur athletes differently. So block for pro status. So divide the sample to pro and amateur, randomly assign the pro athletes to treatment and control, randomly assign amateur athletes to treatment and control. So then your pro amateur status should be equally represented in both groups. Why is this important? Well, what if we had a random sample and then we randomly put people into treatment and control, and because of random chance, we had more pro athletes in one group and more amateur athletes in the other group, then we might get a result that's based on the random chance of our sample being a little bit off. And then we wouldn't be able to replicate it because we do another sample and it might be the opposite, and we get the opposite result. So blocking helps us to try to be able to replicate and find the true causes of things. Okay, so practice question. The study is designed to test the effect of light level and noise on exam performance of students. The researcher also believes that light and noise levels might have different effects on males and females. So wants to make sure both genders are equally represented in each group. Which of the below is correct? So A, there's 3 explanatory variables, light, noise, gender, and 1 response variable, exam performance. Or B, there are 2 explanatory variables, light and noise, 1 blocking variable, gender, and 1 response variable, exam performance. Or is it C, there's 1 explanatory variable, gender, and 3 response variables, light, noise, exam performance. Or are there 2 blocking variables, light and noise, 1 explanatory variable, gender, and 1 response variable, exam performance? Okay, so think about what these words mean. Okay, so explanatory variable should be the one that's causing the thing. And then the response variable should be the one that's affected by the cause. And the blocking variable is the third variable where, or third or fourth, is the other variable where we're looking for, where we think that might have some effect. So we need to equally divide them. Okay. And so the correct answer is 3, 2, 1, B. There's two explanatory variables, light and noise. There's a blocking variable, gender, and one response variable, exam performance. Okay, the difference between blocking and explanatory variables. Okay. Okay, so factors are conditions we can impose on the experimental units. So blocking variables are characteristics that the experimental units come with, but we would like to control for. Okay, so blocking variables are like when you create a sample, and some of them are like this and some of them are like that, and we just want to make sure that there's equal proportions. Set my T flying there. Blocking is like stratifying, except using experimental settings as opposed to observational studies. Okay. Some more experimental design terminology. All right, here's some more vocab words. Placebo as a fake treatment, often used control group for medical studies. And the reason they do that is because for things like getting better from a disease, thinking you're taking a treatment sometimes leads you to get better faster. So there's this thing called the placebo effect. Placebos tend to be 14% effective. There's like 14% of people that if you just gave them sugar pills and told them that this would help them get better, they actually do get better because our human bodies are complicated and weird and lots of things affect them, including like how we feel. Oh yeah, placebo effect. So believing that you're receiving special treatment can sometimes lead to improvement. Blinding is when experimental units do not know whether in the control or treatment group. And then double blind is when the experimental units and the researchers who interact with the patients do not know. And so this double blinding is useful for medical studies where you're afraid that like the doctors and nurses will treat the two different groups differently. So you want them to, if like the nurses are like there's someone in the control group and the nurses are like, I'm so sorry that you're or in the control group they're much more peppy, that could have an effect. So you sometimes need to double blind just because humans are complex and the why we get better from things is super complex. And so double blinding helps isolate that. And so that you can just look at only the treatment. Okay. Here's another practice question. What is the main difference between observational studies and experiments? Is it A, experiments take place in a lab while observational studies do not need to? Is it B, in an observational study, we only look at what happened in the past? Is it C, most experiments use random assignment while observational studies do not? Or is it D, observational studies are completely useless since no causal inference can be made based on their findings? Only one of those statements is true. Which one is it? Okay, and the correct answer is 3, 2, 1. Correct answer is C. Most experiments use random assignment while observational studies do not. Okay, so A is wrong because lots of experiments don't take place in the lab. B is wrong because remember from this last section, there's two types of observational studies. And a retrospective is looking back at the past, but a prospective is setting it up for the future. And then D, observational studies are not completely useless. They point us to things. So if an observational study finds correlation, then maybe we have enough information to get the funding to do a good experiment to see if there's causation. Okay, so observational studies, we want to be careful that we're like correlation is not causation, but also they're not completely useless. They're still useful for some things. Okay, now this is kind of a complicated chart, but it kind of gets to the fact of observational studies do not do not show causation. So random assignment, meaning treatment and control, that's what gives you causation. Whereas random sampling is what gives you the ability to generalize to the whole population. And so in the upper left is perfect, the ideal experiment. Causal conclusion generalized to the whole population. Okay, that's hard to do though. So there's so many things that we can't do experiments for. So for instance, I mean, I don't know. There's coming up, we're going to do one. There's an observational thing we looked at where whether or not men and women are treated differently with their job applications for a bank. And this is looking back in the 1970s. But you can only do that as an observational study because you can't just like make people boom switch genders, right? So you can't just like assign people treatment and control. So a lot of life we only have observational studies for. So for instance, like almost all nutritional stuff is observational studies, not enough of them are experiments. And so that's why nutritional things can change all the time. Like you should eat this, you should not eat that. You should drink this, you should not drink that. It's all observational. So it points towards causation, but it's not proven causation. Okay. Okay. So most experiments, we don't have perfect random sampling because you need to have people sign up for them. And most observational studies, they don't prove causation. And then in the bottom right, bad. So bad observational studies. All right. That completes section 1.4, which completes chapter 1.